Jordan Morgan is a remote iOS engineer for Buffer who lives in Ozark, Missouri. He also writes on his blog, Swiftjective-C, about technical iOS topics and indie development.
All right. I got the hardest part done, figuring out how to mirror my display the right way. So, all right, yeah, so today I'm talking a little bit about optimizing images. So a lot of ground to cover in 10 minutes, so let's just hop right in. So today I'm going to cover basically 3 core topics. The first one is buffers. Kind of what are they at a high level, how do they work on iOS, and why do we need to know about them? Second, we'll talk about UIImage and UIImage view. Of course, those are the main abstractions we use as iOS developers to display kind of rich media in our apps. And as you would expect, those have a very unique relationship with buffers, so then we'll kind of build on that. And then finally, we're going to look at a technique called downsampling. And up to that point, we'll have figured out some ways that these buffers can get us in trouble with memory, and downsampling can help us. So kind of before we go on, here's a picture of my youngest of 3 kids. Her name's Baylor. She's 9 months old now, so a little bit bigger than that. But in particular, pay attention to this image. It's a 266 kilobyte JPEG. So, not a PNG. Don't have to worry with the transparency. So this is a really small image. So it should be perfect to use in our iOS apps, right? Really no problems with it. It's certainly not big, a very small file size. So if we were to make an iPhone app, let's just say a very basic one, that just has an image view and nothing else, and loads it and puts that image into it. We got 2 of them here. They're identical. The one on your right has about a 30% larger image view, but other than that, they're the same thing. And if you were to look at those and someone asked you which one of those is going to use more memory, you would probably look at it and say, well, the one on the right. It's bigger, right? And the answer is a little bit more complicated because they use the exact same amount of memory. And there's a little asterisk there because if you did profile it, you'd see the one on the right does use a tiny bit more, but that's not related to what we're talking about. In terms of image memory and the hit that you take, they were identical. So with that stage kind of set, let's talk a little bit about buffers. Now, you can think of buffer conceptually as just a contiguous region of memory. And like I mentioned earlier, there's 3 buffers that we really need to worry about. That's a data buffer, an image buffer, and a very special buffer that UIKit uses called a frame buffer. So a data buffer is a sequence of bytes, and the ones that we really care about here are the ones that might have an image file associated with it. And that image file has all sorts of metadata associated with it as well, kinds of the ones that you're probably used to seeing, JPEG, PNG. It also says what size the image is. But what a data buffer doesn't have is per pixel information. So UIKit can't use it on its own. And that's why we have image buffers. Image buffers, unlike a data buffer, does have per pixel information. So this is something that UIKit and UIImageView can use. And in fact, they do. The display hardware uses image buffers to actually render what you see at a per pixel point. It illuminates the display. So on the broad topic, you could think of it as an in-memory representation of the image that you're trying to show. Then finally, there's a frame buffer. Now, a frame buffer is a little bit different. A frame buffer is used by UIKit to actually render the output of your own app. So everything you've got in the UI window gets rendered to the frame buffer, or with iOS 13, I guess the scene now. I'm not sure how that really works yet, but what's going to happen with this frame buffer is when it updates, the display hardware actually pulls from it, and that's why you see what you see on your app. It's all coming from the frame buffer. Now, of course, the frame buffer changes a lot. So when you scroll through your app, the frame buffer's updating it, and the display hardware pulls from it, and that's why the pixels change color. Because as a user, you interact with it all the time, and the content has to change, and that's how it works. Because of that, it's not a one-time operation. In fact, this happens at 1/60th of a second. That's why you often hear, to get smooth scrolling, you're trying to hit 60 frames per second. And to do that, there's a lot of things you have to do, but basically the GPU has to keep up with all the things that you're asking the frame buffer to render, and then the display hardware takes it and shows it. And if you think that sounds stressful, well then think of the iPad with ProMotion display. It's twice as fast. That happens at 1/120th of a second. So now that we know about buffers, let's talk about, again, the 2 main abstractions that we use to show rich media content. That is UIImage and UIImageView. And let's take a holistic view of this process here. So we have a UIImage, and this UIImage, as you would expect, has a backing buffer. And when you load in an image, say you pull it from the disk or you download it from the network, we have that data buffer we mentioned earlier. But again, in model view controller fashion, with the model being the image, the view being the image view, it needs to render it. So the image is going to give it its data. But at this point, we just have our data buffer. We don't have an image buffer, so the image view can't use it. So what kind of happens here? Well, there's this hidden step, and it's very, very important to understand, called decoding. And the reason you may not have heard of it is because UIKit does a phenomenal job of abstracting it away from you. So you don't have to think about it a lot of the times. But it does decode, and it turns the data buffer into an image buffer. So now UIKit can understand what the image looks like. The image is going to pass off that image buffer to the image view. It'll render it, and then UIKit copies that into the frame buffer, and finally, it's displayed. So kind of that's the whole round-trip process that we kind of looked at earlier and how the buffers work. So a few important things about decoding that you really need to understand. One, the image buffer size, basically the CPU and memory hit that you're taking, is intrinsically tied to the image's size, right? And also, the frame buffer, as we saw, refreshes all the time. So since this decoding process can be a CPU-intensive hit, UIImage only does it once, right? Because it wouldn't make sense to keep decoding it over and over and over because the frame buffer is going to update a lot of the times. So what this means is you could have a lot of allocations hanging out for if you have a lot of images in your app. And if you remember one thing from this whole talk today, just remember this. Decoding is related to the image buffer size, right? It's not necessarily tied to the image view that you're putting in. That really doesn't matter. It's about the size of the image. So now going back to picture of Baylor here, the image's size in terms of the bytes was kind of a red herring, right? We were looking at the wrong thing. What you really need to look at is the dimensions. And this is a 17 by 80 and 20 by 48 pixel size image. So if we assume 4 bytes per pixel, which is very common, we can do a little math here and figure out that if we do 17 by 80 times 2048 times 4 divided by 1024, 1024, this 266 kilobyte image actually makes an image buffer that's 13.4 megabytes. So that can be surprising if you don't know how decoding works. And of course, if we use the CLI tool VM map, we can run this app. And actually, this is a live summary. I ran VM map on this app. And you can see down at the very bottom, image I/O, in fact, it is 13.4 megabytes. That's exactly how much that's costing us. So again, the size of the image counts, not necessarily the size of the image view that you're putting it into. So with all that, the question really becomes, how do we get a smaller image buffer? Because that's what's going to save us a lot of this memory that we don't need. Or, at the very least, how do we get an image buffer that's equal to the size of the image view we're putting it in? And of course, you do that by downsampling. So to do downsampling, there's a very handy framework in iOS called ImageIO. It does lots of stuff. It can read and write most image file formats. You can access metadata, do color management. Excuse me. But particularly, what it can do is create a thumbnail object. So let's rewind and look at our whole rendering pipeline. You load, you decode, and you render. But now we're going to load, create what's called a thumbnail object, decode that, and then we'll render it. And what this is going to give us is, most importantly, a smaller image buffer size, right? We can really control it at this point. But also, it can discard that original data buffer that was used to create the image buffer in the first place. So we got two big wins here. The good news is the code for this is not too complicated. This is code I took exactly from my own app. And what you want to do is give a URL and basically a max size. So let's step through each one of these. The first thing we're going to do is create this options dictionary. And it has this should cache flag. And what this is telling the framework is, hey, I'm making an object that's going to decode later. But right now, just know that there's something at this file URL that I'm going to need to decode. Just leave it alone. Then we'll move on and create an options dictionary. And from top to bottom, let me pull these through. The image from thumbnail is saying, I want you to create the thumbnail from the original image. So if it's been modified in any way, it doesn't matter. I'm worried about the real image. Cache immediately is very important because, again, kind of in tandem with the last option, when you actually request this thumbnail, you're telling the framework, then decode it. Now that can be really important because if you use something like this in self-row index path, you're going to then, using this technique, get a nice constant demand on the CPU, right? Because iOS does really well with constant demand. What you don't want to do is give it spikes. And then the transform flag is going to rotate and scale according to the image data. And then finally, the most important one is this max size. So you want to calculate this by whichever is greater, the height or the width, and then probably multiply it by the screen scale too. But if you don't include this, you're going to end up decoding the original file size, right? And that defeats the whole purpose of what we're trying to do. Finally, you do one call to image source, create thumbnail at index, pass it the options, and then you can finally wrap that in the familiar UI image, and you're good to go. So what's that going to do? Well, let's go back to our sample app. Before, if you were to profile this, this app was taking 69.5 megabytes just sitting there, loading in the image view, decoding the image, putting it in there. Now, with downsampling, you get it all the way down to 56.3 megabytes. You just saved 13.2 megabytes. That's almost the size of the whole image, actually. That's a huge savings, and that's just one image, right? So if you're hearing this and thinking, when would I use this? If this is so important, why haven't I heard of it before? Well, if you're downloading images from disk, if you can't resize from the server, or you're loading from network calls, it's a good time to do this, especially if the image view that you're putting the image in is smaller than the image. Go for it. But if you're using the asset catalog, you can probably skip this, right? Because the asset catalog compiler has a lot of intelligent things in there that do a lot of this for you. So if you're like me and first heard about this, you tested it on an image from an asset catalog and didn't see any difference. That's why. For further resources, I have a whole blog post on this topic. The WWDC video linked below is where I learned a lot of these concepts. So definitely, if you're more interested in this, go watch that. You'll learn a lot. And finally, if you would like to talk more, I'm at JordanMorgan10 on Twitter. There's my website, and you can see this technique happening live in the app I work on in Buffer. And that's all I got.
So we have time for some questions, if anyone has them.
Hello. Are there any worries or concerns about multi-threading with doing the scaling and downsampling stuff?
Yeah. So in terms of like if you need to do it on the main thread, or like in terms of like if you have like a lot of photos and doing it in self-a-row and like popping that on a background thread. Yeah, so that can be important to think about because you can actually hit this problem called thread explosion. So if you don't do this in a serial manner, you'll actually maybe paralyze your work over a lot of CPUs that don't exist, and then you'll be in a big, you'll have a problem there. So again, what you want is that constant demand on the CPU. You don't want the spikes. So if you do this in self-row and you do kick it off on the background thread, then do it serially and not, spread it out across a bunch of threads.
Do you know what interpolation it uses when downsampling? Is it nearest neighbor, bicubic, bilinear?
I don't actually, no. And probably if you dive into the Image.io documentation, you could probably figure that out. And if you can't figure that out, there's actually several different ways to do this kind of thing. So there could be another framework that offers those options or gives you more control on how that works.
Are there any gains if the size of the image and the image view are the same?
I don't think so, no. I'm not 100% sure on that because I've not actually tried it myself. But if the image view that you're putting it in is the same size as the image itself, then the decoding downsampling I don't think would matter at that point. There might be some other optimizations under the hood that I'm not aware of that you get from downsampling aside from shrinking down the image buffer a bit according to size. So that might come into play, but I'm not 100% sure.
Okay, thank you so much,
Thank
Jordan.
you.